Hi everybody, in this video we are eventually going to learn about vector projections, but before then we're going to go really carefully through all of the prerequisite knowledge. Okay, the first thing that we need to talk about are unit vectors. Now you know this unit vector here, that is one step to the right, and you know we would call him I, and you know this unit vector here, that's one step higher, and we call him J. Now this little hat that they're wearing is the indication to us that they are unit vectors. Okay, we don't put that hat over just any vector. In order to deserve that hat, the vector has to have a length of 1 unit. Have a look at this blue vector over here. This blue vector is 3 steps to the right. We call him 3i because he is 3 lots of the unit vector I. We could think about it as there's 1 of them, 2 of them, 3 of them. Now that's unit vectors just in the horizontal or vertical direction, but we can actually have a unit vector in any direction. Vector u is 3i plus 4j. That means he's 3 steps to the right and 4 steps upwards. There he is there. Vector u is not a unit vector because he is way longer than 1 unit. But we can make a unit vector in the direction of u. That's what that means there. So that's like if we're getting vector u and we're just taking that much of it, that would be a unit vector in the direction of u. It's got the same angle, it's at the same angle as vector u, but it's only 1 unit long. So how do we find a unit vector in the direction of u? Well, what it is vector u divided by the magnitude of vector u. So the magnitude of vector u, we'd use Pythagoras. Remember Pythagoras here? If it's 3 that way and 4 that way, the hypotenuse is that one squared plus that one squared, then the square root of that. So the magnitude of u is 5 units, 9 plus 16, square root of that. So the unit vector in the direction of u is 3i plus 4j over 5. Or we could write 1/5 of 3, 4, or we could write 3/5, 4/5, however we like. They're all equivalent statements. How would we make unit vectors for A, B, and C? Well, let's look at A. The first thing I need is the magnitude of A, and that's going to be the square root of 7 squared plus negative 2 squared, which is the square root of 49 plus 4, which is the square root of 53. A unit vector then in the direction of A will be 7i minus 2j over the square root of 53. Could you pause the video now and find me unit vectors in the direction of B and C? Hopefully you had some success at that. Remember, we can't go on to our new work until these basic concepts are really firm. Well, the magnitude of B is going to be the square root of 4 plus 9, square root of 13. So unit vector B, well, I'm going to write it this way this time. It's going to be 1 over root 13 times that. Well, this C is interesting. What is the magnitude of vector C? Well, it's actually 10, isn't it? Just 10 units. So unit vector in the direction of C is negative 10i divided by 10, which is negative I. Now, if you didn't get all of those 3 correct, you need to do the ones on the next screen. If you did get them correct, it's fine, just continue. Press pause now if you need to. The next thing that we need to revise before we move on is the dot product. Now, we don't need to worry for now about the geometric interpretation of the dot product. You just need to know how to find the dot product of 2 vectors. Here we are. Could you find the dot product of those 2 vectors? How do we do it? Well, what do? We say the first one, the I times the I. 3 times negative 3 is going to be negative 9, and then plus that one times that one. 4 sevens, negative 28. So it's going to be negative 9 plus negative 28. Next, can you find vector A dot vector B? Pause the video. Okay, well, to do this, we have to say that one times that one plus that one times that one. Negative 20. Now you'll notice here that the dot product, also called the scalar product, will deliver us a scalar value. That is just a number. Okay, the dot product takes two vectors and it does a form of multiplication that delivers us not a vector, just a scalar. Okay, have a look at these. Could you pause the videos and find A dot B, B dot C, and C dot A? Okay, let's see how you went. A dot B is going to be that times that, negative 14 plus negative 4 times a half, that's negative 2. Next one, B dot C, negative 7 times 4 plus 1/2 times 3. And C dot A, 4 times 2 is 8 plus 3 times minus 4 is minus 12. Okay, that is the dot product. Now let's do something a little bit more complex. I've given you vectors A and B, and what I need you to find is A dot B hat. So B hat, remember here, this one is a unit vector in the direction of B. How would we go about this? Well, it's going to be vector A dot, now what is B hat going to be? Remember, B hat is vector B over the magnitude of vector B. So that's going to be 4i minus 3j over the magnitude of B. 4 4s are 16, 3 3s are 9s, 25, square root of 25 is 5. So it's going to be A dot B hat. Now, so I could write that's going to be 4 over 5 negative 3 over 5. I could do it like that. But there is another way that may be a bit more simple that I could do. I could do 4 negative 1, that's vector A, dot, then I could just do this one here like that, and then I could put over here, it's going to be 1/5 of that. Because remember we were saying in the last video, if we have some scalar, k, and we've got k lots of A dot B, we can either multiply the scalar through A first, or we could multiply it through B first. We don't do both, of course. Or we could dot A, vectors A and B, and then multiply through the scalar at the end. It doesn't actually matter. I don't really like to see these fractions here. That kind of scares me a bit. It makes me think it's going to be harder than it really is. Okay, so what I'm going to do here is leave this out the front, and I'm going to go, well, scalar product is going to be 4 times 4 is 16, plus negative 1 times negative 3, negative is a positive. It's going to be there. So it's going to be 1/5 of 19, which is 19 over 5. Can you have a go here at finding A dot B hat? Remember, the first thing that you're going to need to do is find what B hat is. Remember, it is vector B divided by the magnitude of B. Press pause. Okay, have a look at how I went about this. My first step was to find the magnitude of B. I said 1 squared plus 1 squared was 2, and I'm after the square root of 2, put that there. And then I just rewrote that in this component form, just make it look a bit nicer. What do I do next? Well, I need to work out A dot B hat. I put A like that, B like that, and look where I put that little scalar. I just stuck it out the front there. That'll make it easier to work with. Next, I'm just going to move it over here. Now I'm going to do the dot product. 5 times 1 plus negative 3 times 1. That is 5 minus 3 is 2 over root 2. Okay, that is A dot B hat. Did you get it right? A little bit different this time. I want you to find B dot A hat. Pause the video. Okay, how did you go with it? Well, I found out what A hat is over here. I'm going to go vector B dot A hat. Well, I'm just going to do A first, and then I'll multiply through the root 40 at the end. So that's going to give me 1 on root 40. Lots of 1, 2 is 2, plus negative 3 times 6 will be negative 18. So that will give me 1 over root 40, lots of negative 16. And I can just simplify up that third a bit, and that'll give me negative 8 over root 10. Now, you could rationalize the denominators if you want to, but for the sake of this, let's just not worry about that. Okay, this next one I want you to do, I want you to find A dot B hat. That there is going to give you a scalar, won't it? And then I want you to multiply that scalar by B hat, which is a vector. You should end up with a vector here. Can you see if you can do this one? Pause the video. Okay, you might be thinking, what the heck is this? I really want you to watch me doing this because there's a few tricks with this algebra I do want you to watch. Okay, first thing I've done is I found what B hat is, and notice here how I've put that on the outside, and I've just kept that on the outside out of the way. Now, next thing I'm going to do is I'm going to find this bit here, vector A dot B hat. That is going to give me this. But watch what I'm doing here. I'm going to leave that 1/5 over there minding its own business. I'm going to dot these two vectors. 1 times 3 is 3, 4 times 2 is 8. 3 and 8 is 11, and then multiply it through there if I want. Okay, now that has got me, this bit here is equal to 11 over 5, and I need to multiply that by vector B hat. Now what is B hat? It is 4, but it's 1/5 of that, isn't it? Now, can you see that by leaving these scalars outside, I can just do this multiplication? So it's actually 11/25 of this, which is going to equal 33 over 25, and then what's that one? 44 over 25. Multiply that through as the last thing, or even, you know what, if you left it like that, that would be okay as well. Okay, here's another one, and I want you to make sure that you can get this right. What I'm looking for is vector A dot B hat multiplied by B hat. Okay, find that for me. Press pause. Okay, so how do I do it? The first thing I do, magnitude of B is root 2. Then B hat is 1 over root 2, lots of this. And I'm certainly not going to multiply that 1 over root 2 through, just to hang with me and you'll see the reason why. Okay, let's work on this part here. So it is 3 negative 2 dot B hat, which is 1, 1. And I need to multiply that by 1 over root 2. Doesn't matter which side I put that on, I'm just doing this part here. I'll add that extra B hat soon. That's going to equal 1 over root 2, lots of, well, 3 times 1 is 3, minus 2 times 1 is minus 2, which will give me 3 minus 2 is 1, 1 over root 2. So this bit here all comes to 1 over root 2. Now I have to multiply that 1 over root 2 by B hat. And what was B hat? It was over here, 1, 1, and then also 1 over root 2. How am I going to do that now? Well, look, I can just say that what's 1 over root 2 times 1 over root 2. Well, it's root 2 times root 2 is actually 2. It's a half, 1, 1. So, or you could write that as I over 2 plus j over 2, something like that. Okay, another one. Work this one out really carefully. press pause on the video. Okay, following my working, looking at this bit here, a dot b hat, and I've worked out what b hat is. It's going to be 5 negative 2 dot 21, and then we're timesing that by 1 over root 5. That equals 10 minus 2 is 8 over root 5. Now the next bit we're after is 8 over root 5 lots of b hat, this one here. And what was b hat? Up here. 2, 1, and 1 over root 5 of that. Now, you can see here that that times that will remove the surd and make it into just a 5. 8 times 1 is 8. So it's actually just 8/5 of this vector here. Remember, this value here is just a scalar. It's just a number, but here we have the vector. So it's 8/5 lots of 2, 1. We could multiply that through and we could say it's 16 over 5, 8 over 5, or we could just leave it like that. It doesn't matter much. So our result that we've gotten here is a vector. Now all of that was just in preparation for us to think about vector projections. Now vector projections are a little bit complex to understand, but I want you to just watch really closely. If we have a vector here, let's call that vector A, and we have another vector here, this one here can be vector B. Sometimes it's useful to define vector A in terms of some amount of vector B and some amount of the vector perpendicular to B. So it can be useful to define this vector here, vector A, in terms of another vector, not just I and J, but in terms of some amount of vector B plus some amount of the vector perpendicular to B. Now if we have, let's just say we've got a Cartesian plane, here's a Cartesian plane here, and we have got a vector that goes up like that. Now we like to define that vector in terms of i's and j's. We can say it's 2i plus 3j. Okay, now we are defining this vector here in terms of I and j. Sometimes we wanted to define a vector in terms of another vector that's not horizontal or vertical. So let me just show you another example. Here is vector A here. Let's say vector B is here. I might want to define A in terms of so much of vector B and then so much of the vector perpendicular to B. You know how I and J are perpendicular to each other? If we are defining a vector in terms of non-I and J vectors, we want to have it in terms of one of them and then the one that is perpendicular to that. So it's like we've made a kind of a slanty I and J situation. Now if we've got that situation here, and if I'm defining A in terms of vector B and a vector perpendicular to B, I call this bit here, see this bit here, this little vector here, I call that bit the projection of vector A onto vector B. This little one is the projection of vector A onto vector B, and sometimes it's called the projection of vector A parallel to vector B. You see this one here, this little vector is some some multiple of B. Here it looks like it's about a quarter of B, doesn't it? Okay, here's an example here. I have vector A 4, 2 and vector B 3, negative 4. Now I could explain vector A as so much of vector B and then a vector perpendicular to B there. Now this little bit of it here, that little fraction of b, I call the projection of vector A onto vector B. And I can find out exactly what that little vector is, okay? Here is the formula. The projection of vector A onto vector B is given by the formula vector A dot B hat multiplied by B hat. Look familiar? So you know how to actually do the algebra of that, don't you? Why don't you pause the video and give that a go? Okay, how are you going? I've got as far as this bit here. Got that bit there equals 4/5. So to finish off the problem, we're after 4/5 of B hat. And what was B hat? 3 negative 4 times by 1/5. So what's that going to be? 4/25 of 3 negative 4. And I've just used my calculator there actually to just find decimal equivalents. And I come up with this vector down here, 0.48, negative 0.64. Now that is the projection of vector A onto vector B. So this little red shaded vector up here should be that. So it should be 0.48, so about half a step to the right. Is that correct? Oh yeah, that looks right, doesn't it? About half a step, 0.48 to the right, and negative 0.64. So 0.64 down, a little bit more than halfway down. And if I had drawn that a bit more exactly, that might look a little bit more correct. This formula here that we've been practicing using unknowingly in the last few slides gives us the projection of vector A onto vector B. It gives us this little bit here. Now once we've got that, we can quite easily work out what this other piece is if we need to know it. But the vector projection of A onto B is that one there. Okay, let's do another example. Vector A is negative 4, 5, and vector B is 6, 1. If I'm looking for the projection of A onto B, well, we have the formula for it, but before we do that, let's spend some time thinking about graphically what it would look like. First up, I need to extend my vector B. So I've just extended a little bit to the left and down. It's like I've got a ruler and put that across there. And what I need to do now, the projection of vector A onto B. Well, what's it going to look like? Well, I could think of A as made up of so much in this backwards direction along B, because I can go backwards on B, that's okay. It's going to be just a negative amount of B, isn't it? And then I need to, at some point, go up at a 90-degree angle in here. So the projection of vector A onto vector B is this bit here, and we use our formula to find out exactly what that vector is. Remember what the formula it is? The projection of vector A onto vector B is given by A dot B hat, lots of B hat. Can you try and work that out really carefully and see if you're correct? Okay, how are you going? I've done as much as this bit here. I've got A dot B hat is negative 19 over 37, root 37, sorry. Now what I need to do now to find my projection is to multiply that by B hat, which is 6, 1, well, it's by 1 over root 37. You see the value in not multiplying that root 37 through, because it should just clear itself up. Remember that root 37 times root 37 is just 37. So it's negative 19, lots of 6, 1. And I just used my calculator there to make those values decimals, just so I can see if it's right. So this says that I am going across 3 and a bit. I've lost my scale here a bit, but if that one there is 6, that looks like 3 and a bit across, doesn't it? And 0.5 down. Yes. So that is the vector projection of A onto B. For these next ones I'm going to put on the screen, what I want you to do is see if you can draw the picture so graphically you can get a bit of an idea about what it actually means. So pause the video and give these a go. Here's the solution to the first one. Pause the video and have a look and see if your answer agrees with mine. I just realised I mislabeled these next two vectors, but pause the video and have a go at this one.